Hi, welcome back. And we're in chapter 3, and more fun, we're in chapter 3, propulsion portion of Kuchmann. So last time we did some derivation of a bunch of equations. I'm actually going to start off again and do just a little bit more on that. As I was kind of writing it down, I felt like maybe I was copying a little bit too much and not kind of getting a little bit more into it. And so I'm going to start off first, and then we'll show you some plots. I want to start off first again and just talk about the propulsive efficiency, maybe just a little bit broader. So in the end, we're saying this is the thing we want, which is thrust, or thrust power. And so that is the thrust force times the velocity that I'm flying at. And what did it cost us? Well, it cost us, Q is the heat added, and then m dot is that we're adding it to the air. Right? So that would represent the heat addition, it's burning our hydrocarbons or burning our hydrogen if you're carrying hydrogen. So that's what we're looking at, right, in terms of cost that. So really, we will split this into two, and so what I'll say is this is the thrust that you're adding compared to the, I'm just going to use in kind of in words, change in kinetic energy, and then that's the kinetic energy to the, what you paid for it. Okay, and so this term we will identify as our jet efficiency, right? So the thrust power compared to the change in kinetic energy, and then this term, which is the change in kinetic energy compared to the heat added, this is our thermal efficiency. Okay, and so first one is actually just look at the thrust power to kinetic. Let's look at the jet term first. Okay, and so thrust is m dot, and then it's v jet minus v0, and then times the v here times that free speed. So that's the thrust, and then the kinetic energy. It's again because the mass flow is roughly the same. Again, even though there's some mass addition of the fuel, it's pretty much negligible. This is then 1/2 the jet squared minus 1/2 the original velocity. Okay, so the mass flow rates cancel out. That's great. And then both of these halves are on the bottom, and so I'll get a factor of 2 up top. And then, so I'm going to just rewrite this now as 2. I'm going to swing the v0 around the other side, and you'll see why here in a second. Vj minus v0. And then what I'm left with here on the bottom is vj squared minus v0 squared. Well, let me factor that. That's the same as vj plus v0 times vj minus v0, right? Because you get the quadratic canceling. Okay, well these two terms cancel, and so then you're left with that 2 v naught over vj, or refactoring that again, you would get vj over v0. So that's where this equation comes from. It always feels a little funny, but again, highlighting what this means is the higher jet efficiency comes from taking a whole bunch of air and only making it slightly different than v0. Now, in the limit where vjet is equal to v0, your efficiency is 100%, but you actually made no thrust, right? Your thrust term went to 0. And so you always have to have some jet velocity that's bigger than v0, but the closer it is to v0, the better. That's why even this has nothing to do with hypersonic flight. So even a big jet engine, you have a big fan that's grabbing a lot of air and barely making it faster. That's actually high jet efficiency. Okay, and then the propulsion efficiency, and so we said it's kinetic energy. Well, the kinetic energy is actually, that change is the same as the change in enthalpy, right? That energy balance that's what we're doing. We're using the change in enthalpy of the states to give us the change in kinetic energy. There's an m dot, because that's a little h, and then that's compared to the m dot q. Okay, so great. Again, the m dots cancel out. That's fantastic. And then this is ideal gas. And so we will then say this is Cp, and the change in energy. So a couple different ones. Okay, there is what it takes to compress it, Even though there's not a pump, I mean, you are using the forward velocity to compress it. So this would be the power taken to compress. It's T1 minus T0. Maybe I'll try down here the state T and S. So we're starting at 0. We're compressing up to 1. We're heat adding up to 2. And then we're expanding to jet. And remember I said that there's sort of our material maximum would be there. Okay. So that's T1 minus T0. Sorry. It's 2 minus jet. And then I have to subtract off the compression side. Okay. And then this is divided by, and it's CP because the Q is what's being added here. And so that's actually then just T2 minus T1. Okay, so this T2 and this T1, and CP's cancel out, great. So that's going to give me a 1, because I'm combining this one and this one. 1 minus, and then this is a plus, so that's a T0 minus TJ. Actually, I always screw that up. It's a minus of a minus. So TJ minus T0 over T2 minus T1. All right, let me clean that up a little bit. Got a little messy. It's a J. Okay, so it's a minus J and then a minus minus, which is a plus 0 minus minus. All right, so we have this. Now, this one will just take one more manipulation. And so, again, we know that because it's the same pressures, we actually know that T2 over Tj is the same as T1 over T0, or written differently, that T jet is equal to T2 T0 over T1. So this term can then also be written as, plugging in jet, T2 over T1 times T0 minus T0 over T2 over T1. Actually, I don't want to split it out just yet. We'll do one more step. Just T2 minus T1. And so I can pull a T0 out front. That's 2 minus 1. So that's T0 times T2 over T1 minus 1. And I'm going to pull a T1 out of this. So it's just T1, and then that's T2 over T1 minus 1. And those cancel out. And so that's then just 1 minus T0 over T1. And, we said that, we showed last time, that's the same, basically 1 plus gamma minus 1 over 2, Mach 1 squared over 1 plus gamma minus 1 over 2, Mach 0 squared. And so, as a reminder, this is eta thermal. And so eta thermal is simply set by the speed you're combusting at compared to Mach 1. And then we had another equation for the amount that you can add is actually set by your maximum minus 1 over 1 minus eta thermal. And so that's how you find what you're able to add. And then the V jet over V0 is then 1 plus 2 over gamma minus 1 Mach 0 squared times that times eta thermal. And then you would plug that into your propellant efficiency. Okay, so those are kind of the three main equations. So I wanted to just walk through that a little bit more, because now we're gonna show some results. Because of all this, we can walk through some of it. Now, the first thing I have to show you, there's this plot in Kuchmann, and I'll be honest, I stared at that for hours, and I had to do a whole bunch of derivations, and I couldn't figure out what he was plotting. The description of the plot is over a couple of pages, so I finally figured it out, and I'm going to split it in a couple of things first, okay? So the first one, the plot that he was showing was for T2 over T0 equals 10, Again, that represents material limits of about 3,500 Fahrenheit. That's roughly where you would want to stop at combusting. And so in each one of these cases, I'm plotting free stream velocity versus the Mach number that you're going to combust at. So this would be versus M1. And the dotted line is the thermal efficiency, so that's just this one up front. And then the solid line below that is the total efficiency, because now I'm also, by setting T2 to T1, I'm finding the Q that I get to add, and I get to then figure out the jet, which means I can solve for the velocity. So, a jet velocity of, jet efficiency of 1 would represent, again, no thrust, but it would be the solid line comes at the top line. So Kuchmann was plotting this a little bit, but he only plotted the dotted lines, and he was showing it on the right. They had some other lines on the left. So in fact, this was the plot that Kuchmann was showing. So the dashed whites were this thermal efficiency, and these other color lines that I'm putting in here to highlight in color were just super confusing. And so let me get rid of the white lines, because again, it's just actually the thermal compression. So actually then I eventually figured it out because I was recreating the plot. These lines represented, hey, I want to put in this much fuel, which is not how you would build an engine, but you're just saying, I want to put in that much fuel. So it's actually coming over here and saying, I want to do this, but I am still having T2 over T0 being 10. So you actually are solving for 8 of thermal, which is a weird thing to say. So once I figured that out, so I've now plotted and added to the plot that, hey, if Q over CT is 8, then your thermal efficiency has to be 5. And then you would back calculate all the rest of the stuff, because I can get, that is my thermal efficiency, and now I can get my jet efficiency and solve it. So that would be your plots, and that would give you your propellant efficiency. I didn't find that a useful plot, but I suppose it was helpful for me to go recreate it. So I now plotted the way that I would look at it. So again, we have this propulsion efficiency, and we actually know that the range equation is going to be driven off of that. So we actually know that writing down the range equation, that's the heating value over G, which I love in that form, but that's 4,400 kilometers, times the efficiency, times the lift to drag of the vehicle, and then 1 minus the amount of fuel I get up to cruise, and then the total fuel. So this is actually the range. And so we're building vehicles that go far. We want them also to go fast, but that's ultimately what we're going to care about. And so first off is then just being, okay, no, hang on, let me just plot this as a function of Mach number, because that's all it is. The thermal efficiency is just a function of Mach number, so that's the dashed line. Super clean, that's it. And I use the combustion speed of 0.5. This is a ramjet, right? I'm not talking about scramjets just yet. And then, actually then know, based on that, you could calculate the temperature that the air is after it's been rammed in, okay? Because that's a material of choices. So it's not that all of these speeds, fine, you could choose all those speeds, but once you hit Mach 4, the air is now 1,200 Fahrenheit, which would then mean, hey, stainless steels or titanium, that's about its limit. So this gray line is everything titanium and steel. What I've highlighted here in blue would be saying, actually, I'm okay making my engine out of Inconel. So this blue actually represents an Inconel range. And then anything past this would be some exotic materials, and then this would be crazy exotic materials to get all the way up to this. So that's your choice. And again, that's why I keep looking at this in material conditions. And this is not even talking about skin temperatures of the vehicle yet. We kind of see this really interesting band between Mach 4 and really that's like Mach 4.7. Okay, that becomes super interesting from a ramjet point of view, right? But that's just the propulsion efficiency. That's just this one part. And then you then take a look at, if you wanted to say, hey, I actually would rather think about this term in terms of ISP, which this is the same term as ISP times V0. Okay, we can plot that, right? I'm really trying to relearn myself to think about in terms of propulsion efficiency, not in terms of ISP, because range is actually, we can actually calculate this. ISP starts becoming this other weird variable that when you're doing the analysis at this level, it's kind of an intermediary. It's actually really fascinating. But here's the ISP if you wanted to do that. Now, I am throwing another efficiency on top of that. So I'll actually multiply this by another number. That's what I'm saying here, 100% versus 80% versus 60% if you wanted to get an idea. So then again, all the three curves where I'm again highlighting the air temperature, because these would be, engineering choices for us to go make. And so you can see what the ISP is for the ramjet. And then the big one is then actually saying, well, I'm really interested in range. Well, that's just this. And so for this plot, I did use the standard definition of L over D, a very conservative one. So it's somewhere between Mach, these are usually what is shown when you're doing L over Ds. That's kind of the, over Mach. Those are kind of some acceptable ways of estimating L over D. So I'm choosing the conservative one when I'm plotting this to get that range. And I'm using kerosene, jet fuel. And so you see also this really interesting curve, which then says, we're trying to target a trans-Pacific vehicle. That's 5,000 miles. Atlantic would be 3,500 miles. And this is 55% fuel at takeoff. Like, that's kind of the upper limit of what we might be comfortable doing. That's a lot of fuel. What I hope you are seeing is there's kind of this roll-off. Like, Mach 4 is roughly at 5,000. And Mach 5 is not really that much better. But it's going to be a significant choice up in terms of materials within the engine and certainly within the vehicle temperatures for not a ton of gain. So again, the physics is saying there's something really interesting here kind of at that Mach 4, or maybe up the Mach 4.7 range. And also just a reminder, this weird definition of hypersonic is Mach 5. Actually, the more accurate definition of hypersonic is where heat is kicking your ass. So I could actually, with a straight face, say, is Venus a hypersonic company? No, Venus actually don't want to be a hypersonic company. I want to be flying really, really fast without heat kicking my ass, right? So we're actually trying to find that edge. And so there's something saying that the edge could be Mach 4, could be Mach 4.7. And, the company that finds the edge, which is then going to keep the price down and the range high, that's who's going to win this. Now, the military might look at this and say, I don't need to fly that fast. I'm actually super okay with a 2,000-mile vehicle. Well, great. And they may want 2,000 miles in Mach 7. Okay, that's a thing the military can do, absolutely. But commercial, we're going to want to take a look at things that look like this. So, I found that really, really powerful to, again, the only assumptions going into this plot, the thermal efficiency is being set by the Mach number, because it's getting that much compression. And then the jet efficiency is being effectively set by the max temperature I'm willing to handle in the ramjet, which is a T2 over T1 of 10. The rest of it then falls out. I then added a 90% factor on top of that just to account for losses or things not being awesome, and then 55% fuel, and then using an L over D. And I am taking to account, like I am solving for this lambda C with some RBCC estimates. Right, so I am accounting for the fact that there's some amount of propellant to get to cruise, and I'm accounting for the fact that there's a glide distance, right? So if you get met to Mach 7, you're going to have a big glide range. Now, I want to highlight the reason these plots are stopping at this weird number here. That's actually the point at which, let me come back to this, that's actually the point at which you can't add any fuel, right? It is after compression at Mach 6 and 0.6 to ramjet, it's already at T2 over T1 being 10. So there's kind of a limit. So you'd have to, if you wanted to do ramjet at Mach 14, you'd have to weigh up your temperature limits. It also then says, if you go redo this with Scram, which is kind of what you're seeing here, you could come back and pick, no, let me go combust at Mach 2. It's going to extend that speed, right? So as opposed to cutting off sort of at shorter Mach numbers, it would get you further down the road. So, all right, that was again really fascinating how you can just get to this simple explanation with just this. So, we'll see you next time for a little bit more on engines. We'll be able to take a little bit of kind of geometry and start looking at flow paths.